Our task was to design an international creative college for 1,500 students. We aim to design a college that can provide students and teachers with a comfortable environment. During the design process, we considered many factors such as local climate, natural lighting, heating, and materials. We attempted to design an energy-saving and low-carbon college that can achieve Passive House certification. The Creative College is in suburban Bristol. Bristol is in the southwest of the UK. Bristol is in a temperate oceanic climate. It is warm during the summer and cool and rainy during the winter. Therefore, the design considered factors such as protection from heavy rainfall, as well as finding ways to provide the best daylight. The design began with the site analysis. As shown in the diagram, the site is located in a quiet environment, surrounded by the residential and green areas. The site is mainly affected by the southwest wind. We decided to use windows at various levels to improve indoor air ventilation. The topography of the site decreases from northwest to southeast. We designed large stairs to allow the students to sit and rest. The traffic is most convenient in the south side of the site, which leads to the city center. The location is suitable for including school gates and introducing bus stops. However, the sound of the nearby traffic may cause noise problems. Therefore, the college was placed at the north part of the site. There are numerous trees in the site which were repositioned around the grounds to prevent noise and air pollution. The concept was based on the shape of a hand. The public rooms of the college were grouped together as a palm, and classrooms scattered like figures. The college consists of a private school, a secondary school, and a shared school. There were three options. In the first option, these three schools are concentrated and connected by a long corridor. In the second option, the schools are separated by each other. In the third option, schools are dispersed but still connected by several corridors. Then we made the three models in SketchUp and entered them into Safari for energy calculation. These calculations revealed the third option to be the most energy efficient. Therefore, we adapted the third model for further design. The classrooms and offices which require high levels of daylight are organized in a stacked layout in the south. The toilets and changing rooms are in a private space in the middle. The shared school includes sports hall, a dining hall, and centers at the north of the building. In addition, the college has external terraces for students and the teachers to rest. The college's large green area and trees support a healthy and comfortable learning environment.
Simulated by the Safari software, the average daylight factor was 2.84%. According to British standard, which stipulates the average daylight factor must exceed 2%, the performance is acceptable. In order to improve the daylight of the space, the skylights and clerestory were designed. Because of the high position, they facilitate daylight in the building. The college is located in Bristol, and according to the wind rose diagram, the wind direction can benefit the building's airflow. In order to reduce the environmental impact, the life cycle assessment was applied. By choosing materials from professional rating system, the environmental impact of the building can be minimized. Manufacturing materials off-site is an effective way to reduce construction waste. Referring to the Green Guide from BRE, the insulated concrete formwork and structural insulated panels were chosen for the external wall and roof. Regarding the acoustic performance of the classrooms, the internal walls were designed to include sound-resistant properties. The window is the component which will cause the largest amount of heat loss. Hence, the low E glazing filled with argon was chosen for reduce the overall U value. The U value of the window was about 0.8 watt per square meter Kelvin. By choosing better construction materials, the envelope's energy performance will improve.
Before we got started with this project, we researched how energy systems in educational buildings work. In terms of renewable energy, we selected solar energy, biomass energy, and ground power, which can be acquired from recycled materials. The sun provides the greatest amount of solar energy to the Earth, therefore we want to make good use of it. We decided to install PV panels on the pitch roof. We also considered solar thermal system for heat loss. Here is the theoretical result from heat loss calculation in the swimming pool. This could be successfully recovered by using the solar thermal system and biomass boiler. We also considered combined heating and power system to increase the efficiency for our building. The biomass energy comes primarily from the school's operational waste, including food, timber, and paper. It can also help students develop good habits regarding reusing waste. In the final stages of the process, we put the building model into Sapphire software, which revealed an overall energy consumption of 16.3 kWh per square meter per year, which is nearly half of the energy consumption in traditional schools. The pie chart we created shows the majority of energy consumption comes from ventilation and lighting equipment. To increase the sustainable level of our building, to meet the demand of passive house, modification of vents and daylight openings are important issues we must consider in future development.